How can a dead star keep getting stronger long after it should have faded away? How can an object no larger than a city consume another star for hundreds of millions of years without ever slowing down? And what happens when it finally becomes too heavy for the laws of physics to hold together? Roughly 5,000 light years from Earth, a neutron star named PSR J0952-0607 is spinning 707 times every second. It contains 2.35 times the mass of our Sun, compressed into a sphere only 20 kilometers, about 12 miles, across. Scientists call objects like this black widow pulsars because they gradually strip material from the companion stars trapped in their gravity, leaving behind little more than a stellar remnant. With every layer it steals, the pulsar grows heavier. With every orbit, its companion grows smaller. The star feeding it was once a normal star. Today, it has been reduced to little more than a fraction of Jupiter's mass, while the dead star at its center continues to spin with astonishing precision. A point along its equator races through space at around 14% of the speed of light, and each rotation sends powerful beams of radiation sweeping across the galaxy like the beam of a cosmic lighthouse. But there is another question hidden inside all of this. Why does this star still exist? According to some of the best models of neutron star physics, it is already approaching the maximum mass such an object should be able to support. Every gram it continues to absorb brings it closer to a threshold beyond which a neutron star can no longer remain a neutron star. No one knows exactly where that limit lies. We make these long form space documentaries because we love this stuff, and so do you. If you want to keep exploring with us, subscribe, and we'll be here whenever you need a quiet journey through the cosmos. The first clue begins with what happens when a massive star reaches the end of its life. Imagine holding a single teaspoon of matter that outweighs every human who has ever lived. That is where our path truly begins. Before we follow a starving companion around a deadly remnant, we need to understand what that remnant really is. Everything starts with a massive star. When a star begins life with at least 8 times the mass of our Sun, it burns through its nuclear fuel at an astonishing pace. For millions of years, fusion pushes outward against gravity. Then the fuel is exhausted. The outward pressure disappears almost immediately, and gravity takes control in less than a second. The collapse is astonishingly violent. The central temperature surges to roughly 100 billion degrees, while the outer layers rebound into space as a supernova. Those expanding clouds will someday help build new stars and planets. At the center, something entirely different remains behind. Atoms no longer survive there. The crushing pressure forces electrons and protons together until they merge into neutrons. What emerges is called a neutron star, the densest stable object known in the universe, containing roughly the mass of our Sun packed into a sphere no larger than a city. Its density stretches imagination. A single teaspoon of neutron star material would weigh about 1 billion tons, comparable to the combined mass of every human who has ever lived. Around that incredible interior sits a crust of solid iron, about 8/10 of a kilometer thick, which is about 1/2 of a mile. Beneath it lies matter that no laboratory on Earth has ever reproduced. The collapse changes motion as well. You can picture a figure skater drawing in their arms while spinning. As their body becomes more compact, the rotation speeds up. A collapsing stellar core follows the same principle, conserving angular momentum as its enormous size shrinks into something only a few dozen kilometers across. The result is a newborn neutron star, turning dozens of times every second, most eventually slow. With each passing age, they lose rotational energy and their pulses grow weaker. Their brilliant youth gradually fades into a far less active existence. That is the expected story, but one remarkable object refused that ending. The pulsar designated J0952-0607 drifted close enough to another star for gravity to begin taking material from its companion. Instead of winding down, it received fresh mass and fresh angular momentum. Every stream of stolen plasma restored energy that time had been carrying away. The dead star found another way forward. From that moment onward, its future became tied to another sun's destruction. The same process that strengthened the pulsar slowly weakened its companion, creating one of the most extraordinary partnerships anywhere in our galaxy, a cycle that continues with relentless precision today. There is a remarkable twist hidden inside this system. Time usually steals energy from a neutron star, slowing each rotation until its once brilliant rhythm gradually weakens across billions of years. We would expect the same ending here, but gravity had another plan. A nearby companion changed everything. As that neighboring star grew older, its outer layers became less tightly bound. Whether passing through a swollen giant phase or reduced to a compact remnant, it began surrendering material into the surrounding space. The escape was only temporary. The neutron star's immense gravity intercepted the drifting gas before it could travel farther into the galaxy. Nothing falls straight down. Every stream of captured matter already carries motion around the neutron star. That motion prevents a direct plunge and spreads the gas into an accretion disk, a rotating ring of infalling material that circles the neutron star before gradually spiraling onto its surface. Friction within the disk heats the plasma to tens of millions of degrees, producing one of the brightest environments found around any stellar remnant. The journey changes both travelers. Each tiny parcel of plasma delivers more than fresh matter. It also carries angular momentum, the rotational motion stored within every orbit. As that momentum transfers onto the neutron star, the rotation becomes faster. Every arrival adds another subtle push. Astronomers call this process recycling. The name describes a pulsar that seemed destined to fade, only to regain strength by drawing material from its companion. Instead of surrendering to age, the dead star acquires new mass, greater rotational speed, and increasing power. You are watching a stellar clock being wound again, one particle at a time, but every gain has a cost. The companion steadily loses the very substance that once allowed it to shine. Matter flows across the narrow gulf separating the two stars, shrinking one while strengthening the other. Their futures become inseparable, linked through an exchange that continues orbit after orbit without interruption. Gravity alone is not enough. The pulsar also unleashes an intense stream of energetic particles and radiation that batters the companion directly. Radiation pressure, meaning the physical push created when light and particles strike matter, strips away additional layers from the outside, even as gravity continues drawing material inward. One force pulls, another blasts away. Together, they erase the companion from opposite directions. The comparison became unavoidable. Astronomers named these systems after the black widow spider because the resemblance matched the physical reality with startling precision. One partner survives by consuming the other until almost nothing remains. For hundreds of millions of years, the pulsar designated PSR J0952-0607 has continued this relentless exchange. Each completed orbit leaves the neutron star slightly heavier and its companion slightly smaller. The balance keeps shifting, grain by grain, until the star that once fed the system has almost entirely disappeared, There is a point where every prediction in physics begins to narrow toward a single boundary. As we follow this pulsar, we eventually arrive there. The numbers stop feeling merely impressive and begin testing the limits of everything our theories allow. Most neutron stars settle into a familiar range. Their masses typically gather around 1 and 4/10 times the mass of our Sun, a region close to the range where collapsed stellar remnants most often reach long-term stability. Beyond that, gravity grows steadily harder to resist, even for matter compressed beyond anything found elsewhere in the universe. Theory draws a line. Physicists call it the Tolman, Oppenheimer, Volkoff limit, the maximum mass a neutron star can support before its own gravity overwhelms every remaining source of internal pressure and forces collapse into a black hole. Exactly where that boundary lies depends on what the unseen interior is truly made of, but current models generally place it between about 2 and 1/2 times the mass of our Sunday. Now compare that with reality. The pulsar designated PSR J0952-0607 has a confirmed mass of about 2 and 35 hundredths times the mass of our Sun, with some analyses allowing values approaching 2 and 1/2 solar masses. That places it at, or extremely close to, the lower edge of the predicted collapse threshold. A motionless star this heavy would not survive. But this one is moving in an extraordinary way. Its rotation creates an outward effect that partly offsets gravity near the equator, slightly reducing the inward compression. The star becomes very slightly wider around its middle, buying itself precious stability through motion alone. Even that has a limit. Astronomers call it the mass shedding limit, the rotational speed where the outward effect at the equator finally balances gravity. Spin any faster, and material would begin leaving the surface instead of remaining bound to the star. This pulsar lives near that frontier. In 2022, a research team led by Roger Romani at Stanford University published the measurement confirming its remarkable mass. Their work showed that this object occupies a region where accepted neutron star physics becomes increasingly difficult to satisfy. The observation answered one question while leaving another untouched. The star exists, but every stream of matter arriving from its fading companion makes the balance more delicate. Each addition increases the gravitational burden while the rotation slowly loses energy over immense spans of time. One trend climbs upward, the other gradually falls away. For now, they remain in equilibrium. Yet you can almost picture those opposing processes advancing toward one another across cosmic history. One keeps adding weight, the other keeps surrendering support. The remarkable stability we witness today depends on both remaining in balance, and the universe has never promised that balance will last forever. Some numbers are too large to understand until we compare them with something familiar. The rotation of this pulsar belongs in that category. We can read the measurement, yet our minds still struggle to picture what it truly means. Begin in an ordinary kitchen. A powerful blender at full speed turns only about 6 or 7 times each second. That already appears remarkably fast to our eyes. Increase that speed again and again, and you reach the spinning blades inside a jet turbine, completing roughly 250 rotations every second. Still, we are not close. The fastest rotating object ever created in a laboratory, a tiny levitated nanoparticle suspended inside a vacuum, reached hundreds of billions of rotations each minute. Even that belongs to a completely different physical scale, involving microscopic particles rather than entire stars. Now, return to the pulsar. The object designated PSR J0952-0607 completes 707 full rotations every second. One complete turn lasts only about 1 and 41 hundredths milliseconds, faster than your nervous system can fully register a single sensation. Its surface barely has time to exist. A point along the equator races through space at roughly 130,000 kilometers every second, which is about 80,778 miles. That is about 14% of the speed of light, placing the star in a regime where the predictions of Albert Einstein's general theory of relativity become directly measurable. Space itself responds. One consequence is called frame dragging, the twisting of spacetime caused by a rapidly rotating, massive object. Near this pulsar, the very geometry surrounding the star is pulled into motion. If you could somehow remain nearby, even your deepest sense of direction would no longer follow the familiar paths we experience around ordinary worlds. But the spin serves another purpose. The magnetic poles do not align with the rotation axis. As the star turns, narrow beams of radiation sweep across the galaxy like the beam from a lighthouse crossing a dark coastline. Whenever one of those beams crosses Earth, our radio telescopes record another pulse. The rhythm is astonishing. Across years of careful observation, the arrival times vary by less than 100 nanoseconds, a span so brief that it rivals, and in many situations exceeds, the precision of many atomic clocks built by human hands. That precision emerges naturally. Extreme mass, extraordinary rotation, and remarkable compactness reinforce one another until they create one of the most dependable timekeepers known anywhere in the universe. Every pulse carries the signature of physical laws operating under conditions almost impossible to reproduce, allowing us to measure a distant dead star with breathtaking confidence while it continues turning beyond ordinary intuition. If we could pass through the surface without disturbing it, every layer beneath would carry us farther from familiar physics. The journey would begin inside matter we still recognize. It would end in a place that has never been directly observed by any instrument built on Earth. The outermost shell still resembles a solid. Its crust consists largely of iron nuclei locked into an immense crystal lattice, compressed so completely that the material bears almost no resemblance to ordinary metal. Even so, the underlying ingredients remain recognizable. We are still dealing with atomic nuclei arranged into an ordered structure. That familiarity soon disappears. As the pressure rises with increasing depth, the nuclei become overwhelmed. Neutrons escape from them in enormous numbers until they dominate the surrounding material. This region is known as the inner crust, where neutron-rich nuclei gradually dissolve into a sea filled with freely moving neutrons. Then geometry itself becomes strange. Near the boundary between the crust and the core, physicists predict the existence of nuclear pasta, a genuine scientific term describing the remarkable shapes formed when surface tension competes against electrical repulsion between atomic nuclei. Instead of remaining spherical, matter organizes itself into broad sheets resembling lasagne, narrow tubes resembling spaghetti, and hollow structures resembling Swiss cheese. These forms exist at densities millions of times greater than anything found at Earth's surface. They are astonishingly resilient. Calculations suggest nuclear pasta may be the strongest material anywhere in the universe when compared across the same cross-sectional area, surpassing every known substance by enormous margins. Yet, even this extraordinary layer may only be a transition towards something stranger. Below it lies uncertainty. The central core reaches densities greater than those inside an atomic nucleus. At that point, our most successful physical theories no longer agree with one another. We know the matter must exist. We do not yet know its true form. One possibility is a neutron superfluid. A superfluid is a state of matter that flows without internal friction, allowing neutrons to move with zero viscosity while exchanging angular momentum only loosely with the solid layers above. Another proposal suggests the particles themselves dissolve into a quark-gluon plasma, where quarks move freely through an intensely energetic fluid, unlike anything that has existed in large quantities since the first moments after the Big Bang. But an even more unusual idea remains. Some physicists argue the core may contain strange quark matter, including a type of fundamental particle called the strange quark. If correct, this material could prove more stable than ordinary nuclear matter under these immense pressures. These possibilities are not interchangeable. Each predicts different maximum masses, different stellar sizes, and different behavior under gravity. The confirmed mass of PSR J0952-0607 already rules out every model unable to support such an enormous neutron star. The object before us is more than a distant remnant. It has become the only laboratory capable of revealing which description of matter nature ultimately chose. Long before any telescope on Earth detected this remarkable object, its message had already begun crossing the galaxy. The radio pulse we eventually received departed roughly 5,000 years earlier, when many human societies were still rooted in their earliest agricultural traditions, completely unaware that such a beacon even existed. The signal simply kept traveling. Its destination turned out to be the low-frequency array, a radio observatory spread across 24 countries and built from approximately 20,000 individual antennas working together. Rather than relying upon one enormous dish, the observatory combines many widely separated receivers into a single instrument of extraordinary reach. That approach has a name. It is called aperture synthesis, a technique that combines signals collected by distant antennas to simulate a telescope whose effective diameter matches the greatest separation between them. In this case, that virtual telescope stretches across more than 2,000 kilometers, which is about 1,243 miles, giving astronomers a level of detail impossible for any single antenna to achieve alone. The discovery itself came without expectation. Astronomers were conducting a systematic survey of the galactic plane, carefully searching through immense collections of radio data instead of pursuing one predicted target. Hidden among countless natural radio sources, the repeating pulses eventually revealed themselves through careful analysis. Distance emerged from timing. Each pulse reached Earth, with lower radio frequencies arriving slightly later than higher ones because free electrons scattered throughout interstellar space delayed them by different amounts. This effect is known as the dispersion measure, a frequency-dependent delay caused by those free electrons. A larger dispersion measure means the signal encountered more electrons, indicating a greater distance traveled through the galaxy. But radio waves told only part of the story. Astronomers then turned to the W.M. Keck Observatory in Hawaii, where an enormous mirror measuring 10 meters across, which is about 33 feet, gathered the faint light coming from the pulsar's companion. That mirror consists of 36 precisely aligned hexagonal segments, working together with astonishing accuracy. At Earth's surface, The companion produced only about one detected photon each second. Even that was enough. Observations followed the companion through complete orbits, lasting about 9 and 4/10 hours. As it circled the pulsar, its brightness changed, and the wavelengths of its light shifted slightly toward shorter or longer values, depending upon whether it moved toward Earth or away from us. Those shifts carried hidden information. The changing speed along our line of sight is called the radial velocity curve, a measurement derived from the Doppler effect, the stretching or compressing of light caused by motion. Combined with the orbital geometry, those measurements revealed the mass ratio between the two stars. From observatories standing beneath Earth's atmosphere, astronomers measured the mass of an object smaller than Manhattan, located about 5,000 light years away, with a precision of roughly 17 hundredths of the mass of our Sunday. That achievement remains one of modern astronomy's finest demonstrations of careful observation. Every orbit leaves behind another small change. No single revolution transforms the companion beyond recognition, yet over hundreds of millions of years, those tiny losses accumulate into a portrait of a star gradually disappearing from the universe. What remains today is only a fraction of its former self. The companion now contains about 2/100ths of the mass of our Sun, roughly 20 times the mass of Jupiter. It is the surviving core of what was once a complete star, reduced by an extraordinarily long history of gravitational transfer and relentless exposure to the pulsar beside it. Its two hemispheres live under remarkably different conditions. The face that always points toward the pulsar reaches about 9,000 Kelvin, heated continuously by the stream of energetic particles and radiation pouring across the narrow gap between them. Turn to the opposite hemisphere, and the temperature falls to about 5,000 Kelvin, almost identical to the surface temperature of our own Sunday. One world carries two climates. The pulsar has transformed one side into a far hotter environment, while leaving the opposite face close to ordinary stellar conditions. This contrast is far more than an interesting detail. The changing temperatures alter the companion's brightness throughout each orbit, allowing astronomers to reconstruct the system's orientation and calculate the masses of both stars with remarkable precision. But the escaping material follows more than one path. Only part of the gas pulled from the companion ultimately reaches the pulsar. A substantial portion is driven outward again by the pulsar's powerful radiation and particle wind. Where these opposing flows collide, they create an intrabinary shock, a glowing sheath of intensely heated plasma surrounding the pair and producing detectable emissions in the form of energetic X-rays. Its shape tells another story. The shock does not form a perfect ring around the system. Instead, it bends away from the companion and sits noticeably offset from the orbital center. That asymmetry reveals the ongoing contest between the pulsar wind, a continuous outflow of energetic particles, and the evaporating gas streaming away from the shrinking companion. Each orbit briefly hides the pulsar. As our line of sight passes through the expanding cloud, the familiar radio pulses weaken or disappear altogether. These eclipses are irregular rather than sharp, because the surrounding gas remains turbulent, constantly shifting in density and structure, instead of forming a smooth envelope. Nothing about the process is fixed. The cloud changes from one orbit to the next, forcing astronomers to watch carefully as each pulse fades, scatters, and gradually returns. Those variations provide another window into conditions inside this extraordinary binary system. Some black widow companions eventually become no more massive than large planets, representing the final remnants of stars almost completely consumed. The companion of PSR J0952-0607 appears well along that same path. If the system remains intact across the coming billions of years, the feeding will eventually end. The pulsar will continue spinning hundreds of times each second, carrying its remarkable precision through the galaxy with no companion left beside it. Every balance in nature has a limit, even when that limit remains hidden for millions of years. Somewhere in the future of this remarkable pulsar lies a final moment. We do not know when it will arrive. We understand only the conditions that will eventually make it unavoidable. The trigger could take more than one form. Additional matter from the fading companion may gradually push the star beyond the Tolman, Oppenheimer, Volkoff limit. Its rapid rotation may also continue slowing until the outward support provided by spin can no longer compensate for the crushing pull of gravity. Both processes may reach their critical point together. The ending comes swiftly. The interval is measured in milliseconds rather than days, hours, or even seconds. A neutron star, roughly 19 kilometers across, which is about 12 miles, containing more than twice the mass of our Sun, suddenly loses the ability to support itself. Gravity immediately becomes the only force that matters. There is nowhere left to resist. The collapsing matter falls inward toward the Schwarzschild radius, the critical distance where the escape velocity equals the speed of light and the boundary of a black hole forms. For a body with this mass, that radius is roughly 6 kilometers, which is about 3.7 miles. The star contracts through only a few remaining kilometers before an entirely different object exists. But the process is not an ordinary explosion. Many theoretical models predict that the outer layers are not blasted dramatically into space. Instead, the entire structure folds inward upon itself with extraordinary speed until an event horizon surrounds the collapsing matter. The transformation is governed by gravity rather than outward violence. Perspective changes the story. To a distant observer, the final light appears increasingly stretched toward longer wavelengths by the immense gravitational field. This effect, known as gravitational redshift, gradually delays and weakens the escaping radiation. The pulsar seems to slow as its last visible signals struggle against the growing curvature of spacetime. Yet for an imaginary observer carried with the surface, the collapse finishes without delay. The universe notices. If the collapse is even slightly uneven, it should produce a brief burst of gravitational waves, ripples traveling through spacetime itself. Those waves would differ from the longer signals produced when two compact objects spiral together before merging. Some models also predict a short burst of gamma rays, lasting less than 2 seconds as the newborn black hole settles into equilibrium. Then the pattern ends. The familiar radio pulses simply cease. The beam that swept across our planet for thousands of years never returns. Astronomers monitoring its exquisitely regular timing would record one final pulse, wait for the next, and find only absence. They would understand immediately that one of the lightest known black holes, containing between roughly 2 and 3 times the mass of our Sun, had replaced the extraordinary star that once occupied that distant corner of the galaxy. Sometimes the most important discovery is not an object, but an absence. As astronomers compared the masses of collapsed stars over many decades, they noticed an unexpected pattern that refused to disappear. The distribution seemed incomplete. Neutron stars consistently appeared below roughly 2 times the mass of our Sunday. Confirmed black holes, meanwhile, generally began above about 5 solar masses. Between those two populations stretched an interval where almost nothing had been confidently identified. This became known as the mass gap. No one knew whether the gap reflected a genuine law of stellar evolution or merely the limits of our observations. Perhaps nature rarely created compact objects within that range. But another possibility remained equally compelling. Those objects might exist in substantial numbers while escaping detection because they produced little light or appeared only under unusual circumstances. Then this pulsar entered the picture. With a confirmed mass of about 2 and 35 hundredths times the mass of our Sun, PSR J0952-0607 occupies the lower edge of that long debated region. It approaches a boundary where neutron stars were once thought unlikely to survive, forcing theorists to reconsider where the true upper limit may actually lie. Another clue arrived soon afterward. In 2019, the Laser Interferometer Gravitational Wave Observatory detected a remarkable gravitational wave event known as gravitational wave 190814. The signal came from the merger of a black hole containing about 23 solar masses with another compact object whose mass measured approximately 2 and 6 tenths times the mass of our Sunday. Its identity remains uncertain. If that smaller object was a neutron star, it exceeded the maximum mass predicted by many accepted models at the time. If it was a black hole, it became the lightest confirmed member of that family, occupying a region where black holes had rarely been observed before. Either answer changes the picture. The confirmed existence of PSR J0952-0607 already raises the minimum value. Any successful theory must allow for the greatest possible neutron star mass. As that boundary moves upward, the range of possibilities for the mysterious companion in gravitational wave 190814 becomes narrower and increasingly informative. But the implications reach much farther. The mass gap may conceal an entire population of compact objects born through gradual collapse rather than dramatic stellar explosions. A neutron star that slowly gains enough mass could eventually cross its final limit and become a low-mass black hole without producing the spectacular displays normally associated with black hole formation. Such transformations could pass almost unnoticed. No brilliant supernova need announce the event. No enduring cloud of glowing debris must remain behind. In many cases, there may be only a brief burst of gravitational waves before the new black hole continues drifting through the galaxy. If that pathway is common, thousands of these elusive objects may already wander among the stars, carrying almost no visible sign that they were ever neutron stars at all. A remarkable irony emerges as we continue this journey. The same extraordinary stability that allows a rapidly spinning pulsar to survive near its physical limits also transforms its entire class into the most precise natural clocks known anywhere in the universe. Every pulse marks time. Some millisecond pulsars maintain such remarkable regularity that the arrival of their radio pulses changes by less than 100 nanoseconds across many years of continuous observation. A nanosecond is 1 billionth of a second, an interval so brief that light travels only about 30 centimeters, which is about 1 foot, during that time. Their consistency rivals, and in some cases even exceeds, the precision achieved by the finest atomic clocks built by humanity. That precision serves a greater purpose. Astronomers combine observations from carefully selected millisecond pulsars into what is called a pulsar timing array. Rather than studying each star independently, they monitor dozens of these celestial clocks scattered across the sky, comparing their pulse arrival times with extraordinary care. Together, the pulsars become a detector spanning the entire galaxy. But what are they trying to detect? The target is a gravitational wave, a ripple traveling through spacetime itself, gently stretching and compressing the fabric of the universe as massive objects accelerate. Unlike the brief bursts produced during violent collisions, the lowest frequency gravitational waves evolve with astonishing patience. Some require many years to complete a single cycle because they originate from pairs of supermassive black holes containing millions of times more mass than any object we have followed in this story. No instrument on Earth is large enough to measure such immense waves directly. Instead, astronomers watch the clocks. As a gravitational wave passes between Earth and these distant pulsars, it changes the apparent arrival times of their signals by incredibly small amounts. The shifts are not random. They appear across the sky in a distinctive relationship known as the Hellings-Downs curve, a mathematical pattern that links timing changes between different pulsars according to their positions. The evidence gradually accumulated. The North American Nanohertz Observatory for Gravitational Waves regularly monitors 68 pulsars, including several exceptionally stable millisecond pulsars. After many years of observations, the collaboration announced in June of 2023 compelling evidence for a gravitational wave background, a persistent hum created by countless gravitational waves overlapping throughout the universe. But the discovery did not stand alone. The European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Indian Pulsar Timing Array each reported matching evidence through completely independent observations. Together, the results strongly suggest that thousands of pairs of supermassive black holes in distant galaxies are slowly orbiting toward eventual mergers, filling the cosmos with an immense gravitational chorus. The detector that revealed this astonishing background was not assembled from steel, glass, or silicon. It was built from long dead stars whose perfectly measured pulses continue crossing the galaxy, allowing us to sense movements of spacetime itself. In the autumn of 1967, a doctoral student named Jocelyn Bell Burnell spent long days examining endless rolls of chart recordings from a radio telescope outside Cambridge. She was 24 years old and only 7 months into her doctoral research when a tiny, irregular mark repeatedly caught her attention. It occupied only a few millimeters on the paper, yet it refused to behave like ordinary interference. Something was different. The instrument stretched across roughly 4½ acres, built from thousands of poles and wires rather than a single dish. Its purpose was to monitor faint radio sources across the sky. Among those observations appeared a signal arriving with astonishing regularity, separated by 1 and 3300 seconds every single time. Nothing in known physics fit that pattern. Her supervisor, Anthony Hewish, initially considered the possibility of an equipment problem. That was a sensible first explanation. Scientific instruments can produce misleading signals, and extraordinary claims demand careful skepticism. But repeated observations continued producing the same, precise rhythm from exactly the same point in the sky. The mystery deepened. Within the research group, the source received the temporary label Little Green Men 1. The name reflected a genuine working hypothesis rather than a joke. At that moment, no accepted natural process could explain perfectly repeating radio pulses arriving from deep space. For several weeks, the possibility of an artificial transmission remained worthy of cautious consideration. But another discovery changed everything. A second pulsing source appeared in a completely different region of the sky. Two independent civilizations broadcasting nearly identical signals from unrelated directions seemed far less believable than a single natural explanation waiting to be uncovered. The search therefore shifted away from extraterrestrial intelligence and toward unknown astrophysics. The answer proved even more remarkable. In 1968, Thomas Gold proposed that the pulses originated from rapidly rotating neutron stars whose radio beams swept across space like cosmic beacons. Many astronomers remained unconvinced at first, but additional discoveries soon followed. The Vela pulsar and the Crab pulsar were each found within well-known supernova remnants, establishing the connection between neutron stars and these repeating signals beyond reasonable doubt. Recognition eventually arrived, although not without controversy. Antony Hewish received the Nobel Prize in Physics in 1974, marking the first Nobel Prize awarded for observational astronomy. Jocelyn Bell Burnell, whose careful attention first revealed the unusual signal, was not included among the recipients. That decision has remained one of the most widely discussed debates in the history of the Nobel Prizes. Her influence continued nonetheless. She later received the Breakthrough Prize, the Oppenheimer Prize, and the Royal Medal. Rather than keeping the approximately $3 million Breakthrough Prize award, she donated the entire sum to support physics scholarships for students from groups historically underrepresented in the field. The faint pulses she noticed on those paper charts became the starting point for every discovery we have explored, including the extraordinary star whose remarkable heartbeat still reaches us across the galaxy. The surface of a neutron star may appear unchanging from afar, yet beneath that appearance, enormous mechanical stresses continue building with every passing rotation. Even after millions or billions of years, the solid outer crust never reaches perfect equilibrium. Forces within the star constantly pull, twist, and reshape it. The strain continues accumulating. Even the comparatively modest magnetic field of a millisecond pulsar applies physical torque, meaning a twisting force, to the rigid iron crust. That stress is far smaller than the magnetic forces found in the most extreme neutron stars, yet it never truly disappears. Across immense spans of time, tiny distortions gradually become significant. Some neutron stars experience a far more dramatic version of this process. They belong to a class called magnetars, whose magnetic fields can reach about 10 raised to the power of 15 Gauss, many trillions of times stronger than Earth's magnetic field. Eventually, the accumulated stress exceeds what the crust can support. The solid surface suddenly ruptures and settles into a new arrangement. This event is known as a starquake, a rapid fracture and readjustment of the neutron star's crust that releases an immense burst of energy. Its scale is almost beyond comparison. The strongest earthquakes ever recorded on Earth reached approximately 9.5 on the Richter scale. A typical starquake corresponds to an estimated magnitude of about 32. The crust itself may shift by only about 1 millimeter, a distance smaller than the thickness of a coin. Yet, within matter compressed to neutron star densities, that tiny movement releases more energy than every nuclear weapon ever constructed by humanity. But the most valuable information arrives afterward. Astronomers detect brief changes called glitches, sudden increases in a pulsar's rotation rate that interrupt an otherwise astonishingly regular sequence of pulses. These events are not observational errors. They are direct messages from deep beneath the crust, revealing that something inside the star has changed. The explanation reaches into unfamiliar physics. Beneath the rigid exterior lies a superfluid of neutrons, a state of matter that flows without internal friction. In many neutron stars, this superfluid continues rotating slightly faster than the crust above it. When the crust fractures, some of that stored angular momentum the rotational equivalent of momentum carried by spinning objects, transfers outward and briefly accelerates the surface. Two extraordinary states of matter become linked. The solid crust and the frictionless interior exchange rotational energy through this sudden coupling, allowing scientists to infer properties that cannot be measured directly. The size of each glitch and the time required for the pulsar to recover place important limits on the behavior of the hidden superfluid. But Black Widow pulsars add another layer to the story. Their long history of accreting matter changes the distribution of stress throughout the crust, producing glitch behavior that differs from isolated pulsars. Every unexpected change in their otherwise perfect rhythm therefore becomes another opportunity to investigate matter under conditions that exist nowhere else in the known universe. On the 27th of December, 2004, at 21 hours, 30 minutes, and 26 seconds, Coordinated Universal Time, a magnetar known as SGR 1806-20 experienced one of the most violent eruptions ever recorded. The event began with a catastrophic starquake, a sudden fracture of the star's solid crust that released an unimaginable amount of stored magnetic energy. The source lay far away. Its home was roughly 50,000 light-years from Earth, on the opposite side of the Milky Way. Even across that immense distance, the outburst crossed the galaxy at the speed of light and reached our planet carrying astonishing power. During only 1/10 of a second, the magnetar released more energy than our Sun emits across approximately 250,000 years. Earth responded immediately. The burst partially ionized the lowest region of the ionosphere, called the D layer, a portion of the upper atmosphere that strongly influences long-wavelength radio transmission. For a brief period, radio communications using those frequencies were disrupted across the nighttime side of our planet. A dead star had altered conditions in Earth's atmosphere from the far side of the galaxy. Spacecraft felt it as well. Several space telescopes, designed specifically to survive harsh cosmic radiation, received more energy than their instruments could measure accurately. Their detectors became saturated, meaning the incoming radiation overwhelmed their ability to record additional signals. Some instruments were temporarily blinded and required several minutes before normal observations could resume. But distance saved us. Scientists estimate that if this same magnetar had been only about 10 light-years away, a distance comparable to some of our nearest stellar neighbors, the consequences would have been profoundly different. The intense radiation could have stripped away a significant fraction of Earth's protective ozone layer. Without that shield, far greater amounts of ultraviolet radiation from the sun would have reached the surface, damaging photosynthesis, disrupting food webs, and potentially triggering a global biological crisis. That possibility reaches into Earth's distant past. Some researchers have suggested that an ancient gamma-ray burst or magnetar eruption may have contributed to the end Ordovician mass extinction roughly 440 million years ago, when approximately 85% of known marine species disappeared. The evidence remains incomplete, yet the hypothesis demonstrates that distant astrophysical events may sometimes influence the history of life itself. The eruption of December 2004 became the most thoroughly measured extreme astrophysical event ever observed up to that time. Today, the closest confirmed magnetar, known as XTEJ 1810-197, lies about 8,000 light-years away and remains inactive. No known magnetar exists close enough to threaten Earth. Even so, astronomers have confirmed about 30 magnetars throughout the galaxy, with many more likely awaiting discovery, spending long ages between eruptions before briefly reminding the universe that they are still there. On the 17th of August, 2017, instruments separated by continents detected a faint ripple passing through spacetime. The Laser Interferometer Gravitational Wave Observatory and Virgo Gravitational Wave Detector measured the signal, arriving from about 130 million light-years away within the galaxy known as New General Catalog 4993. Its pattern was unmistakable. Unlike earlier gravitational wave discoveries, this signal did not come from two black holes. The changing frequency revealed two neutron stars spiraling together during their final moments before collision. Their immense gravity distorted space-time until the stars finally merged into a single, compact object. The story continued almost immediately. Only 1 7/10 seconds after the gravitational wave reached Earth, the Fermi Gamma Ray Space Telescope detected a short burst of gamma rays arriving from the same direction. For the first time, astronomers observed both gravitational waves and electromagnetic radiation from the same cosmic event, allowing two completely different ways of studying a single collision. But the universe had one more surprise. Within 11 hours, optical telescopes located a new point of light that had not previously existed inside New General Catalog 4993. Astronomers identified it as a kilonova, a brief astronomical event produced when two neutron stars merge, powered by the radioactive decay of newly created heavy elements formed during the collision. Its appearance kept changing. The kilonova brightened rapidly before fading across roughly 2 weeks. During that time, its color shifted from blue toward deep red as different freshly synthesized elements dominated the emitted light. Spectroscopic analysis, the study of light separated into its individual wavelengths, revealed unmistakable chemical signatures from elements including strontium, barium, and europium. The observations also provided compelling evidence for the creation of gold, platinum, and uranium. This confirmed a prediction that had waited almost 60 years. The collision demonstrated the rapid neutron capture process, a sequence of nuclear reactions in which atomic nuclei absorb enormous numbers of neutrons before they can decay. Such conditions exist only during extraordinarily violent events involving matter already rich in neutrons. The merger scattered an estimated 16,000 Earth masses of gold into the surrounding region of space. The implications reach all the way to us. Before this observation, astronomers debated whether ordinary supernova explosions alone could explain the abundance of heavy elements throughout the cosmos. The evidence from this single event established neutron star mergers as one of the primary cosmic forges where many of those elements are created before dispersing into interstellar clouds that eventually form new stars and planets. Everyday objects carry that history. The gold in a wedding ring, the platinum inside a catalytic converter, the iodine concentrated within the human thyroid, and the uranium used in nuclear reactors, all began their existence in extraordinary collisions like this one. And if PSR J0952-0607 eventually becomes part of such a merger after its long future evolution, its own matter may someday help forge another generation of heavy elements, enriching distant worlds that have not yet begun to form. In January of 1992, Alexander Woljan and Dale Frail announced the first confirmed discovery of planets orbiting a star beyond our own Sunday. The host was neither young nor ordinary. It was a millisecond pulsar known as PSR 1257+12, located about 2,300 light years away, which is about 2,300 light years, because the distance is already expressed in light years within the constellation of Virgo. The discovery surprised everyone. Astronomers had long expected the first exoplanets to appear around stable main sequence stars resembling our own Sunday. Instead, the honor belonged to a rapidly spinning neutron star, an object born through one of the most destructive events in stellar evolution. Three planets were eventually confirmed, with masses of approximately 2/100ths, 4 3/10ths, and 3 9/10ths times the mass of Earth. They belong to a category commonly called super-Earths, planets larger than Earth, but substantially smaller than the ice giants. Their existence immediately posed a deeper mystery. How could any planet remain after the supernova explosion that created the pulsar? Such an explosion should have devastated the original planetary system, blasting nearby worlds apart or hurling them into interstellar space. Yet these planets clearly existed, forcing astronomers to consider entirely new pathways for planetary formation. Several possibilities remain under investigation. One leading idea suggests that debris from the supernova settled into a rotating disk surrounding the newborn pulsar. Over immense spans of time, that material gradually clumped together, producing a second generation of planets built from the remains of a dead star. Another hypothesis proposes that a companion star was gradually consumed, leaving behind material that later condensed into planetary bodies. But this system is no longer unique. Another confirmed pulsar planetary system surrounds PSR J0952-0607 plus 3120. At least two planets, several times more massive than Earth orbit, that pulsar with periods of about 1 9/10 years and 3 6/10 years. Even so, pulsar planets remain extraordinarily uncommon. Out of roughly 5,700 confirmed exoplanets, only about 15 orbit pulsars, representing well under 1% of the known total. Their environments are unlike anything familiar. Many follow highly elongated elliptical orbits instead of nearly circular paths, preserving evidence of their violent origins. Intense streams of X-rays and gamma rays continually wash across their surfaces. Magnetic fields, vastly stronger than Earth's, surround the system, while the pulsar beam sweeps overhead hundreds of times every second. No known form of life could survive under such relentless conditions. Yet the broader lesson remains astonishing. Planet formation endured the most catastrophic transformation a star can experience. Rather than ending the story, stellar death supplied the raw material for another beginning. These unlikely worlds suggest that whenever enough matter gathers together under gravity, the universe repeatedly finds new ways to build planets, even in places that once seemed completely impossible. At the center of this entire story lies a problem that modern physics has not yet solved. What is the equation of state of dense nuclear matter? Everything we have learned from neutron stars ultimately points back to that single unknown. The phrase sounds abstract. An equation of state is the mathematical relationship connecting pressure, density, and temperature within a material. In practical terms, it is the rule that predicts how matter responds when conditions change. Compress a substance, heat it, or squeeze it harder, and the equation tells us how it behaves. For familiar materials, those relationships are well understood. Scientists have tested equations of state for gases, liquids, plasmas, and ordinary solids through countless laboratory experiments. But neutron stars exist in an entirely different regime. Their interiors reach densities greater than 100 trillion grams within every cubic centimeter, comparable to the density inside atomic nuclei. No laboratory on Earth can reproduce those conditions, and no planned particle accelerator will approach them. Theory, therefore, fills the gap. Different mathematical descriptions predict dramatically different neutron stars. A soft equation of state assumes matter compresses relatively easily. Such models produce smaller stars, lower maximum masses, and in some cases suggest cores dominated by quark matter, meaning particles no longer remain confined inside individual neutrons. A stiff equation of state predicts the opposite. Matter strongly resists compression, allowing larger radii, higher maximum masses, and interiors remaining primarily neutron-rich. But nature has begun choosing between them. The measured mass of PSR J0952-0607, approximately 2 and 35 hundredths times the mass of our Sun, immediately eliminated every soft equation of state that predicted collapse below that value. Many theoretical models that once appeared entirely reasonable could no longer describe the real universe. Another source of evidence soon joined the search. Since 2017, the Neutron Star Interior Composition Explorer has operated aboard the International Space Station. Rather than looking inside a neutron star directly, it observes hot regions on the surface as they rotate into and out of view. Careful analysis of those changing X-ray pulses allows astronomers to estimate the star's radius with remarkable precision. Each new measurement sharpens the picture. A measured mass provides one point. A measured radius provides another. Together, they narrow the range of possible equations of state until fewer theoretical descriptions remain compatible with observation. Current measurements from the Neutron Star Interior Composition Explorer, combined with the exceptional mass of PSR J0952-0607, favor a moderately stiff interior consistent with ordinary nuclear matter or a hybrid containing some quark matter, while strongly disfavoring stars composed entirely of quark matter. That answer extends far beyond neutron stars. It defines how matter behaves under the greatest pressures the universe naturally reveals. Since no experiment on Earth can enter this extraordinary domain, these distant stellar remnants remain the only laboratory where nature performs the experiment for us. Our galaxy contains somewhere between 200 billion and 400 billion stars. Only a small fraction began life with enough mass to collapse into neutron stars. Even so, that modest percentage implies the Milky Way now holds roughly 1 billion to 2 billion neutron stars scattered throughout its spiral arms and central regions. Almost all remain unseen. Fewer than about 3,000 have been detected as pulsars. The overwhelming majority no longer produce radio beams that cross Earth's path, have cooled beyond the reach of present thermal X-ray observations, or travel through space without a companion supplying fresh material. They continue their journeys without announcing their presence to distant observers. Yet they are still there. Each is roughly the size of a city, carrying the compressed remains of a once brilliant star. Although their nuclear furnaces have long ceased operating, their extraordinary density remains unchanged. They drift through the galaxy as enduring relics of stellar evolution, preserving matter under conditions found nowhere else that we can directly observe. But they rarely stay where they were born. When a massive star explodes as a supernova, slight asymmetries in the explosion can launch the newborn neutron star away at tremendous speed. Astronomers call this a natal kick, meaning the remnant receives a powerful impulse during its formation. Many neutron stars travel hundreds of kilometers each second, which is about hundreds of 62 miles each second. Some have gained enough velocity to escape the Milky Way entirely, beginning solitary journeys through intergalactic space. Others have crossed our neighborhood. Across billions of years, thousands of ancient neutron stars have likely passed through the broad region occupied by our solar system. Their distances remained comfortably interstellar, leaving only negligible gravitational influence upon the planets. Most passed unnoticed, neither glowing nor accreting matter, becoming invisible travelers among the stars. Black holes share that hidden population. Current estimates suggest our galaxy contains roughly 100 million stellar mass black holes. Unless material falls inward and releases energy, they emit almost nothing detectable. Between the luminous stars stretches an unseen population of collapsed remnants that greatly outnumbers the brilliant suns defining the night sky. Among the known pulsars, only about 40 have been confirmed as Black Widow systems. They represent rare opportunities to witness the recycling process while it is still unfolding. Many hundreds more almost certainly exist, their beams sweeping across directions that never intersect Earth. But our view is about to expand dramatically. The square kilometer array, now under construction and expected to achieve full scientific operation during the early years of the 2030s, is projected to discover roughly 20,000 additional pulsars. That extraordinary increase will reveal Black Widow systems at many different stages of evolution. It may even capture one whose regular pulses cease during a planned observation, preserving the moment when one of the galaxy's most remarkable stellar remnants finally reaches its ultimate transformation. Only about 1,000 light-years separate Earth from the pulsar, known as PSR B 0833-45, which is less than one-fifth of the distance to PSR J 0952-0607, better known as the Vela Pulsar, after the southern constellation of Vela. It is the closest and brightest confirmed pulsar visible from our planet. Its pace feels almost gentle. The Vela pulsar completes roughly 11 rotations every second. That is far slower than the extraordinary Black Widow pulsars we explored earlier, yet its proximity has made it the most intensively studied pulsar in the southern sky. Every observation adds another piece to a story that remains unfinished. Its birth was witnessed. Astronomers estimate the star exploded about 11,000 years ago. For several days, the supernova would have rivaled the brightness of the full moon in Earth's sky. Human beings almost certainly saw that astonishing display, although no surviving written record describes the event. Today, the expanding remnant still glows across space, stretching over roughly 8 degrees of the sky. If your eyes could perceive its full extent at once, it would appear about 16 times wider than the full moon. But the greatest surprise arrived very recently. During 2023, the High-Energy Stereoscopic System, an array of imaging atmospheric Cherenkov telescopes in Namibia, detected gamma rays from the Vela pulsar with energies reaching about 20 trillion electron volts. These are the highest energy photons ever confirmed from any pulsar. Their origin deepened the mystery. The radiation comes from a region extending roughly 7/10 of a light-year away from the pulsar itself. That distance corresponds to nearly 15 million times the separation between Earth and the Moon. Instead of emerging only from the immediate surroundings of the neutron star, these extraordinary particles are being accelerated far beyond the region where existing theories expected such extreme energies to appear. No current explanation fully succeeds. Researchers continue investigating whether the pulsar wind, a continuous stream of charged particles flowing outward from the neutron star, magnetic reconnection, a process where twisted magnetic field lines rapidly rearrange and release enormous energy, or shock acceleration along the outer boundary of the surrounding nebula, can account for these observations. Each possibility explains part of the evidence, yet none reproduces every measured property. Meanwhile, the star continues evolving. Its magnetic field remains about 2 trillion times stronger than Earth's, even after 11,000 years of gradual decay from the far greater strength present at its birth. That immense field still shapes the energetic environment surrounding the pulsar, driving processes that astronomers are only beginning to understand. The Vela pulsar reminds us that the death of a massive star is never a finished chapter. Long after the original explosion has faded from memory, the compact remnant continues, revealing new behavior, challenging established theories, and showing that the universe still holds discoveries hidden inside objects we believed we already knew. The extraordinary mass of PSR J0952-0607 is compressed into a sphere only about 19 kilometers across, which is about 12 miles. Under such extreme conditions, the familiar rules of everyday experience give way to the predictions of Albert Einstein's general theory of relativity. Time itself changes. Gravitational time dilation is the slowing of time within a strong gravitational field. The deeper an object lies inside that field, the more slowly its clocks advance compared with clocks located farther away. This is not merely a theoretical idea. It has been confirmed through atomic clocks placed at different altitudes, through the operation of global positioning system satellites, and through decades of timing measurements involving binary pulsars. Near this neutron star, the effect becomes unmistakable. A clock resting close to the surface would tick measurably more slowly than an identical clock far from the star. Even at a position roughly 10 kilometers above the surface, which is about 6.2 miles, time would pass by approximately 20% more slowly than it does for an observer near Earth. The closer you approached, the greater the difference would become. Light also carries the signature of gravity. As light escapes from the intense gravitational field surrounding a neutron star, its wavelength stretches toward the red end of the spectrum. Astronomers call this gravitational redshift, meaning the light loses energy while climbing away from the gravitational well. By measuring this subtle shift in neutron star spectra, researchers can estimate how compact these remarkable objects truly are. But gravity reaches beyond the neutron star itself. Its white dwarf companion circles only a few hundred kilometers away, which is about a few 162 miles away. Deep within the system's gravitational field, the companion's own clocks also run more slowly than ours. Precise calculations of its orbit cannot rely upon Isaac Newton's laws alone. Corrections from general relativity become essential for accurately predicting every revolution. Those corrections have already transformed astronomy. The binary pulsar, known as PSR B1913 plus 16, provided the first direct measurement of orbital energy carried away by gravitational waves. Those waves are ripples in spacetime produced by accelerating massive objects. The measured orbital decay matched the predictions of general relativity to better than 0.2%, a result recognized with the Nobel Prize in Physics during 1993. The same process continues here. PSR J0952-0607 and its companion steadily emit gravitational waves, slowly losing orbital energy as the companion spirals inward. That gradual inward drift unfolds far more slowly than the expected approach toward gravitational collapse, yet both processes occur together. Meanwhile, The pulsar's astonishing rotation of more than 700 revolutions each second drags space-time itself. This phenomenon, called frame dragging, gently twists the surrounding geometry, revealing that even empty space cannot remain untouched beside one of the most extreme objects in the universe. The future of PSR J0952-0607 appears to lead toward gravitational collapse, yet the timetable remains profoundly uncertain. Current models allow a span ranging from millions of years to billions of years before the star finally crosses the threshold beyond which no stable neutron star can exist. That uncertainty extends to us. Will human civilization endure long enough to observe that moment? If it does, will our instruments become sensitive enough to recognize every stage leading toward the collapse? Those questions remain entirely open, resting as much upon our own future as upon the evolution of the pulsar itself. Present technology already offers part of the answer. If a neutron star collapsed within only a few hundred light years of Earth, existing gravitational wave observatories could detect the resulting burst of ripples passing through spacetime. At a distance of roughly 5,000 light years, however, the signal from PSR J0952-0607 would be extraordinarily faint, pushing beyond the practical reach of today's instruments. But new observatories are already being planned. The proposed Einstein telescope, a third-generation gravitational wave observatory currently undergoing site selection in Europe, is designed to achieve roughly 100 times the sensitivity of today's laser interferometer gravitational wave observatory at the frequencies relevant to compact stellar remnants. At that level of performance, a collapse occurring 5,000 light years away could very likely become detectable. Other instruments would contribute different pieces of the story. The Square Kilometer Array will measure the pulsar's radio pulses with unprecedented precision, allowing astronomers to monitor tiny changes in its rotation rate and estimate how rapidly additional mass continues accumulating. Future successors to the Neutron Star Interior Composition Explorer are expected to refine measurements of neutron star radii, revealing subtle structural changes as accretion gradually reshapes the star. Meanwhile, the James Webb Space Telescope is already capable of studying the companion white dwarf in infrared light, tracking its continuing thermal evolution as material is steadily removed. Imagine those observations converging. One day, every instrument could be watching the same system. The radio pulses arrive exactly as predicted, until one expected pulse never appears. At nearly the same time, gravitational waves spread outward from the collapse, followed by a brief flash of gamma rays. The pulsar timing signal ends forever because an event horizon has formed, preventing every later pulse from escaping into the universe. Such an observation would never be repeated. Astronomers would directly measure the mass at which collapse finally occurred, identify the precise threshold separating neutron stars from black holes, and record gravitational waves produced during the birth of a new event horizon. The universe occasionally presents moments like these, singular events that happen only once, leaving behind evidence that can transform our understanding for generations to come. When PSR J0952-0607 finally crosses the threshold separating neutron stars from black holes, it will leave behind one of the lightest stellar mass black holes ever expected to form. Its mass will likely remain between about 2 and 3/10 and 2 and 5/10 times the mass of our Sun, preserving almost everything the neutron star accumulated during its long existence. The transformation itself is remarkably restrained. No brilliant explosion is expected to announce the birth of the black hole. If any material from the companion white dwarf still survives, gravity will gradually draw that matter into an accretion disk, meaning a rotating ring of gas spiraling inward. Yet the radiation produced will differ from what came before, because the solid surface that once released energy after each impact will no longer exist. Instead, there is only an event horizon. An event horizon is the boundary surrounding a black hole, beyond which escape becomes impossible. It is neither a physical surface nor a solid wall. It is a region defined entirely by the geometry of space-time. At that boundary, the escape velocity equals the speed of light. Beyond it, every possible future path leads farther inward, and no signal can return to the wider universe. Its size is astonishingly small. For a non-rotating black hole with roughly 2 and 35 hundredths times the mass of our Sun, the event horizon would have a radius of about 3½ kilometers, which is about 2.2 miles. But this object is unlikely to remain motionless. After rotating more than 700 times each second throughout its life as a pulsar, much of that spin may survive the collapse. That changes the geometry. A rotating black hole is known as a Kerr black hole, meaning its rotation twists the surrounding spacetime. Outside the event horizon lies the ergosphere, a region where the dragging of spacetime becomes so strong that nothing can remain stationary with respect to distant space. Every object is compelled to rotate along with the black hole itself. Even energy can escape. Physicist Roger Penrose proposed that the ergosphere allows a theoretical process through which rotational energy can be extracted from a spinning black hole. Known as the Penrose process, it demonstrates that the rotation is not permanently locked away, even though the event horizon itself remains uncrossable from the outside. Afterward, the black hole simply continues. It follows the same path through the galaxy already traced by the pulsar, carrying the same motion and responding to the same gravitational landscape. Passing stars and drifting clouds will notice only its gravity. Almost every other sign of its existence will have vanished. The final chapter extends beyond imagination. Over roughly 10 to the power of 54 years, the black hole will slowly lose energy through Hawking radiation, an extraordinarily gradual quantum process. Compared with that span, the present age of the universe, about 13 and 8 tenths billion years, becomes almost impossible to use as a meaningful measure of time. After that unimaginable duration, the final burst of evaporation will unfold in only microseconds, ending a story that began inside the heart of a massive star. Neutron stars do not exist as isolated curiosities suspended in space. They are engines within the long history of the Milky Way, continually influencing the chemical evolution of the galaxy that eventually gave rise to us. Their work begins before they are born. Every supernova that leaves behind a neutron star also scatters the products of that star's lifetime into the surrounding interstellar medium. Carbon, oxygen, silicon, iron, and many other elements forged through nuclear fusion spread outward, mixing with enormous clouds of gas and dust drifting between the stars. Those clouds become nurseries. Over immense spans of time, gravity gathers this enriched material into new molecular clouds. Inside them, fresh generations of stars begin forming, carrying within their interiors the chemical inheritance of much older suns. Each generation builds upon the one before it, gradually increasing the abundance of heavy elements throughout the galaxy. Our own story emerged from that process. The Sun belongs to roughly the third or fourth generation of stars. The iron within Earth's core, the calcium in your bones, and countless other atoms surrounding us today were forged inside at least one, and very likely several, ancient stars before becoming part of the solar nebula about 4 and 6 tenths billion years ago. Long before our planet existed, those atoms had already completed extraordinary journeys through earlier stellar lives. But some elements followed an even longer path. The gold and platinum found on Earth were created during collisions between neutron stars, including events like the gravitational wave source observed during 2017. Matter produced during such mergers survived 2 complete stellar lifetimes before eventually becoming incorporated into our solar system. The iodine required by the human thyroid, the barium used in medical imaging, and the europium, helping modern electronic displays produce vivid colors, all trace their origins to neutron star mergers. These events remain uncommon. Astronomers estimate that the Milky Way experiences one neutron star merger roughly every 10,000 to 100,000 years. That pace makes each event individually rare. Yet across approximately 13 billion years of galactic history, the accumulated number of mergers naturally explains the heavy element abundances measured throughout our galaxy. This places PSR J0952-0607 within a much larger story. It is neither a historical relic nor merely an astronomical curiosity. It remains an active participant in the continuing enrichment of the Milky Way. If it eventually forms a black hole and later merges with another compact companion, the resulting explosion will distribute newly created heavy elements into surrounding interstellar space. Those atoms will continue traveling. Material, now locked inside this remarkable system, may someday become part of distant molecular clouds, future planets, or forms of life that do not yet exist. This is neither symbolism nor poetic coincidence. It is the combined outcome of chemistry, gravity, and orbital mechanics operating patiently across billions of years, linking the most extreme objects in the universe to every generation that follows. Determining the mass of PSR J0952-0607 required observatories separated by oceans, decades of technical progress, and a level of precision that almost defies intuition. Astronomers were attempting to weigh an object only about 19 kilometers across, which is about 12 miles, from a distance of roughly 5,000 light-years, or about 29 quadrillion miles. The investigation began with radio waves. The low-frequency array stretches across Europe as a network of about 20,000 individual antennas distributed among many countries. Operating between roughly 10 and 250 megahertz, it detects radio pulses that have crossed thousands of light-years while being subtly delayed by clouds of charged particles drifting through interstellar space. Correcting for those delays allows each pulse to be timed with astonishing precision. But radio timing alone was not enough. Astronomers also needed to observe the faint companion orbiting the neutron star. That challenge led them to the W.M. Keck Observatory atop Mauna Kea in Hawaii, standing about 4,145 meters above sea level, which is about 13,600 feet. At that elevation, the atmosphere is thinner and steadier, allowing sharper observations of distant objects. Even then, Earth's atmosphere still distorts incoming light. To overcome that problem, the observatory uses adaptive optics, a system that measures atmospheric blurring in real time and continuously reshapes a mirror to cancel those distortions. A laser projected into the sky creates an artificial guide star using light with a wavelength of 589 nanometers, giving the system a stable reference for every correction. The companion revealed another clue. Its atmosphere absorbs specific wavelengths of light, creating dark spectral absorption lines. As the companion travels toward and away from Earth during its orbit of about 9 and 4/10 hours, those lines shift through the Doppler effect, meaning motion changes the observed wavelength of light. The displacement is measured in angstroms, units so small that each represents only 1/10 billionth of a meter, which is about 3.9 billionths of a foot. Precision became everything. Astronomers measured changes corresponding to radial velocities of roughly 1 kilometer each second, which is about 6/10ths of a mile each second. Calibration against precisely known spectral lines produced by neon and argon inside the instrument ensured those measurements remained reliable throughout years of observations. But the final answer emerged only after everything was combined. The orbital motion provided a mathematical quantity called the mass function, relating the masses of both stars and the orientation of their orbit. The orbital inclination was constrained by modeling the uneven heating across the companion's surface together with the shape of the radio eclipse. Blending those results with the pulsar's orbital parameters finally yielded the individual masses. Years of accumulated observations from multiple facilities converged into a single remarkable conclusion. The universe proved not merely observable, but knowable through patience, cooperation, and measurements of extraordinary precision. The light reaching your eyes from the pulsar designated PSR J0952-0607 tonight began its journey about 5,000 years ago. As those first photons departed, the earliest cities were rising across Mesopotamia, and human civilization was only beginning to leave enduring marks upon history. We never see the present. The pulsar whose mass, rotation, and companion we have measured exists before us exactly as it was 5 millennia in the past. Every pulse we record, every spectrum we analyze, and every orbit we calculate belongs to that earlier moment. Whether the star has already crossed its final threshold and become a black hole remains unknown. If that transformation has already occurred, the evidence is still traveling toward Earth at the speed of light and will not arrive for another 5,000 years. Distance becomes history. Every astronomical observation is an observation of the past. The farther away an object lies, the deeper into time we are looking. Space does not merely separate us from distant stars. It preserves earlier chapters of the universe, allowing different ages to remain visible all at once. The pattern extends far beyond our galaxy. The Andromeda Galaxy, visible to the unaided eye beneath dark skies, appears as it existed about 2.5 million years ago. At that time, the ancestors of modern humans were shaping simple stone tools across Africa. Looking still farther, the James Webb Space Telescope has detected the distant galaxy designated Jade's GSZ 140, observed as it existed only about 290 million years after the Big Bang. At that stage, the universe had reached only about 2% of its present age. Every greater distance reveals an earlier cosmos. The observable universe can be imagined as a series of enormous concentric spheres surrounding us. Each layer represents a different era, preserved because light requires time to cross the immense distances between galaxies. Looking outward and looking backward become exactly the same act. But the process resembles something surprisingly familiar. Astronomy becomes a form of archaeology. Our observatories serve as careful brushes, photons become ancient artifacts, and the sky itself forms a layered record extending across about 13.8 billion years of cosmic history. Every observation uncovers another surviving fragment from a different age. Within that immense archive, the pulsar designated PSR J0952-0607 occupies a comparatively recent layer. Yet even this nearby neutron star remains separated from us by the full span of recorded human history. The radio pulse that first revealed its existence departed while the earliest known writing systems were only beginning to appear. Before that same signal finally reached Earth, Sumerian cuneiform, Egyptian hieroglyphics, the script of the Indus Valley Civilization, and the earliest Chinese writing traditions had risen, changed, and in some cases disappeared. Throughout every one of those centuries, the pulsar continued its unwavering rhythm, untouched by human history and patiently awaiting discovery. The pulsar designated PSR J0952-0607 has no awareness that we are watching it. Its rapid rotation carries no sensation. The steady loss of material from its companion brings no anticipation. Even its gradual approach toward the greatest masses known for neutron stars unfolds without expectation or purpose. It simply follows nature. Every change within this remarkable system arises through the combined action of the four known fundamental forces. Gravity shapes the orbit and compresses matter beyond ordinary imagination. Electromagnetism governs the charged particles racing through intense magnetic fields. The strong nuclear force binds the particles inside atomic nuclei, while the weak nuclear force allows certain particles to transform into others through radioactive processes. No additional force is required. No hidden intention appears within the equations. Yet the result is astonishing. From only these four interactions emerges a system of extraordinary intricacy. A companion star surrenders matter, an accretion disk, a broad ring of orbiting material, channels that matter inward. Powerful magnetic fields redirect the flow toward the neutron star. A lighthouse beam sweeps across space with unwavering regularity. Where energetic outflows collide with material from the companion, an intrabinary shock, a turbulent region where opposing streams crash together, forms and releases enormous amounts of energy. Each process follows naturally from the same underlying laws, but complexity does not require design. The behavior of this single object allows physicists to test how matter responds under pressures and densities that no laboratory on Earth can reproduce. Every successful observation narrows the possibilities for what may exist inside the hidden core of a neutron star, bringing us closer to understanding matter itself. The universe never promised such understanding. It existed for about 13 and 8/10 billion years before you arrived to observe it, and its future stretches across intervals so vast that ordinary language begins to lose meaning. Nothing suggests these laws were arranged for human comfort or curiosity, but they can still be discovered. In 1915, Albert Einstein introduced the general theory of relativity, describing gravity as the curvature of space and time rather than an invisible force acting across empty distance. More than a century later, those equations continue to predict the orbital behavior of pulsar pairs with an accuracy better than about 0.2%. At even smaller scales, quantum chromodynamics, the theory describing how quarks and gluons interact through the strong nuclear force, places powerful limits on what may occur deep inside this remarkable star. That agreement invites reflection. Mathematics developed on one small world correctly describes a city-sized stellar remnant about 5,000 light-years away, which is about 29 quadrillion miles. Whether this correspondence reveals something profoundly remarkable about reality, or simply reflects that only a universe governed by consistent laws can produce observers capable of recognizing them, remains unanswered. Either possibility leaves us facing a cosmos whose indifference is matched only by its extraordinary order. A single lifetime is remarkably short when measured against the age of the universe. Yet within that brief span, you can watch humanity transform distant mysteries into measurable reality, one careful discovery after another. The pace has been extraordinary. In 1967, a 24-year-old graduate student named Jocelyn Bell Burnell noticed an unusual pattern tracing across a chart recorder. That faint signal became the first known pulsar, revealing an entirely new class of celestial object. A few decades later, in 1992, astronomers announced the first confirmed planets beyond our solar system. They were not circling a familiar star. They were orbiting a pulsar, proving that planetary systems could survive events once thought completely destructive. But the discoveries continued. In 2017, instruments built to detect gravitational waves measured the passing distortion created by two merging neutron stars. Within hours, observatories around the world captured the fading light from that collision. Spectroscopic analysis, the study of light separated into its individual wavelengths, confirmed that enormous quantities of gold and many other heavy elements had indeed formed during the merger, resolving a question that had remained open for decades. The story did not stop there. In 2022, researchers combined years of observations from the low-frequency array across Europe with measurements from the W.M. Keck Observatory in Hawaii. Together, they determined that the pulsar designated PSR J0952-0607 possessed the greatest reliably measured mass yet found for a neutron star, resting at the very edge of what current physics appears able to support. Another milestone soon followed. In 2023, astronomers studying an array of precisely timed pulsars distributed throughout our galaxy detected the long-expected background of gravitational waves produced by pairs of supermassive black holes orbiting one another across the universe. Individual neutron stars became parts of an immense natural observatory stretching across the Milky Way. Each achievement came from people. Many of those researchers will never witness the full consequences of their work. They build instruments, refine theories, challenge one another's conclusions, and leave future generations to continue the search. Scientific understanding grows in this way, accumulating across lifetimes rather than within them. Only a century ago, the universe appeared far smaller. In 1924, Edwin Hubble demonstrated that the Andromeda Nebula was a separate galaxy, expanding humanity's view beyond the Milky Way. The neutron star itself was proposed in 1933 by Walter Baade and Fritz Zwicky, then finally confirmed through observation in 1967. Gravitational waves, predicted by Albert Einstein in 1916, remained undetected until 2015. None of this knowledge arrived fully formed. Every measurement in this journey was earned through better instruments, careful analysis, persistent disagreement, repeated testing, and countless revisions. The engineers who built the low-frequency array, the teams maintaining the W.M. Keck Observatory, the scientists operating the Neutron Star Interior Composition Explorer, and the researchers developing orbital models rarely appear at the center of the story. Yet without their patient work, this remarkable star would still be only another point of light beyond our reach. At this very moment, somewhere within the Milky Way, another Black Widow pulsar may be approaching the final chapter of its long evolution. Its companion has already been reduced to little more than a planetary mass remnant, a fading fragment of the star it once was. Thin streams of plasma continue to escape, while the neutron star draws them inward with relentless consistency. The rotation never pauses. Perhaps it turns 600 times each second, perhaps 700, perhaps even 720. Its radio beam continues sweeping across space with unwavering rhythm. Yet, no observatory on Earth may be watching. No telescope can point toward an object whose existence has not yet been recognized. The pulses pass unnoticed, crossing the galaxy until, one day, they may intersect an instrument prepared to receive them. But that moment is never guaranteed. A future survey could uncover the system. The square kilometer array may eventually reveal it through observations of extraordinary sensitivity. An observatory that has not yet been conceived could detect its signal decades from now. Or the neutron star may cross its final physical limit before anyone realizes it was there, completing its story beyond every human record. The galaxy contains every stage at once. Some Black Widow systems have only recently begun stripping material from their companions. Others have already consumed much of the original star, leaving only a small fraction behind. Still others have removed the companion entirely, producing isolated millisecond pulsars that continue spinning long after their partners have disappeared. Across several billion years, the complete life cycle unfolds, while we observe scattered examples preserved at different moments, like separate pages from one immense cosmic history. But you belong to that history as well. The carbon within your body formed inside ancient stars. The oxygen carried through every breath was forged during stellar evolution before being released into space. The iron flowing through your blood was created under conditions that existed long before Earth formed. Even the calcium within the bones surrounding your ears was synthesized inside a star that reached the end of its life before the sun had begun to shine. Nothing here is separate. The atoms that became planets, oceans, mountains, and living cells were recycled through generations of stellar birth and stellar death across billions of years. Eventually, those same atoms assembled into nervous systems capable of recognizing patterns, building telescopes, writing mathematics, and imagining objects far beyond ordinary experience. Through them, the universe gradually became able to examine itself. So, as you consider the pulsar designated PSR J0952-0607, about 5,000 light years away, which is about 29 quadrillion miles, you are not looking outward from a place apart. You are witnessing one part of an unfolding cosmos contemplating another. The universe is not something standing beyond your reach. Its history flows through every atom around you and through every thought that carried us to this remarkable star. Time changes meaning when we follow this story beyond the lives of stars. The familiar markers of history gradually disappear, replaced by intervals so immense that even ordinary language begins to lose its footing. The universe is still young. Its present age is about 13 and 8/10 billion years. Against what is expected to come, that span represents only an early chapter. About 5 billion years from now, our own sun will exhaust the hydrogen, sustaining its core, and begin its transformation into a red giant. Long before then, the pulsar designated PSR J0952-0607 may already have crossed the threshold beyond which no neutron star can remain stable. But that transformation is only another beginning. The black hole left behind will possess a history measured across timescales, requiring an entirely different sense of duration. While galaxies continue evolving, stars will still be forming for vast stretches of time. Eventually, however, even the smallest and longest-lived red dwarf stars will consume the last of their nuclear fuel. Roughly 100 trillion years after the beginning of the universe, the final starlight within the Milky Way will fade. Darkness continues to change. Astronomers describe the following epoch as the degenerate era, a period when white dwarfs, neutron stars, and black holes become the dominant remaining objects. White dwarfs slowly cool. Neutron stars gradually lose their rotation. Black holes continue orbiting through galaxies that have become increasingly empty. Motion remains, gravity remains. Time continues its patient work, but matter itself may not endure forever. Some theories suggest that protons, the particles forming the nuclei of ordinary atoms, may eventually decay into lighter particles. This process has never been observed, and its existence remains uncertain, yet if it occurs, it would unfold only after roughly 1 decillion years or more. By then, nearly every familiar structure composed of ordinary matter would have dissolved into radiation and elementary particles. Even then, black holes remain. Occasional mergers and the absorption of stray energy allow them to persist across intervals almost impossible to comprehend. Only through Hawking radiation, a gradual quantum process predicted by Stephen Hawking, do they slowly lose mass. A stellar mass black hole descended from PSR J0952-0607 may require about 1, followed by 67 zeros years to disappear completely. Supermassive black holes at the centers of galaxies endure even longer, surviving for about 1 Google years, a number written as 1 followed by 100 zeros. After that, almost nothing changes. The universe continues expanding while scattered photons, neutrinos, and perhaps gravitons drift ever farther apart. Temperatures approach absolute zero. Remaining differences in energy slowly disappear, bringing the cosmos toward thermodynamic equilibrium, the state in which no useful energy remains to power further change. This gradual outcome is known as the heat death of the universe. As you think once more of the pulsar spinning tonight, hundreds of times each second, you are considering an object whose journey reaches almost to that unimaginable horizon. While we exist within the remarkably brief and fortunate interval between the universe's beginning and its projected end, at this moment, while these words are being spoken, the pulsar designated PSR J0952-0607 is still turning. 707 complete rotations pass every second. Its beam continues sweeping across the galaxy. Its companion surrenders another immeasurably small fraction of its remaining mass. The rotation slows by an amount far too small for human senses to notice, while the neutron star gathers a little more matter into its extraordinary interior. The process never pauses. Much of the underlying physics is understood with remarkable confidence. The broader timeline is not. Astronomers can describe how gravity, dense matter, and magnetic fields shape this system, yet they cannot say precisely when the final transition will occur. That uncertainty is not a weakness in science. It is an honest description of where knowledge presently stands. But the unanswered questions have become more precise. One of the greatest remaining challenges is determining the equation of state of dense nuclear matter, the mathematical relationship describing how matter behaves when compressed beyond anything achievable in laboratories on Earth. Solving that problem will require the masses and sizes of many more neutron stars, future detections of gravitational waves from merging systems, and perhaps direct observation of a neutron star crossing the boundary into a black hole. More discoveries will follow. The uncertain mass range separating the heaviest neutron stars from the lightest black holes may eventually become clear through observation, or it may reveal entirely unexpected behavior that requires new physical ideas. The discovery of the gravitational wave background during 2023 has already opened another path of investigation, and its full implications remain only partly understood. The galaxy itself is becoming an observatory. Arrays of precisely timed pulsars continue increasing in sensitivity as new instruments join existing networks and observations accumulate across many years. Dead stars have become some of the most powerful tools for exploring the largest structures in the universe, allowing us to measure phenomena that would otherwise remain hidden. Every answer creates another question. That is how genuine knowledge grows. It does not end with certainty. It expands through careful measurement, patient disagreement, improved instruments, refined mathematics, and the determination to examine the universe again after every new discovery. The first pulsar entered human awareness because a young researcher named Jocelyn Bell Burnell noticed an unexpected pattern in her data. The most massive known neutron star was measured because researchers from many nations combined years of radio observations with optical spectroscopy gathered from a mountaintop observatory in Hawaii. Neither achievement was guaranteed. Both depended upon people choosing to keep looking. And so, the pulsar continues spinning. The light continues traveling. The instruments continue waiting. Sleep well, knowing that the signal, leaving this remarkable star tonight, will cross space for about 5,000 years before reaching another observer. Whoever or whatever receives, it will learn exactly where, in its long journey, this star was during this very night. While we paused for a brief moment to wonder alongside it,